to the One World Combinatorics on Words seminar. Our speaker today is Ella Krawczyk from the University of Vienna and Jagiellonian University, and she's going to speak to us about quasi-fixed points of substitutions.
Okay, so thanks, Narat, for introduction, and thank you organizers for inviting me to give, I think, the last talk of this semester on the seminar. So I hope I will manage to keep it brief and not very technical. Okay, so I would like to start with an example, and my example will be a well-known substitution. This is a period doubling substitution. So this is a substitution of constant length 2, send 0 to 0, 1, 1 to 0, 0. And I can look at the fixed point of this substitution, which is an example of a two automatic sequence, since the substitution had constant length 2. Okay. Yeah, so what I want to look at is the following combinatorial object, which I will denote x phi, where phi was the substitution, and its definition is as follows. So I look at all sequences over my two-letter alphabet such that the language of this sequence is contained in the language in the original fixed point x. Okay, so all the finite words which appear in Z have to appear somewhere in X. So if someone likes symbolic dynamics, this, in other words, this object is just the orbit closure of this fixed point under the shift map. When the shift map, I denote by T, and it just shifts my sequence once to the left. Okay, and once we have this set, once we have this set, one can do the following thing. So let's put a total order on my set A. So in this instance, I say that 0 is smaller than 1, and ask how the lexicographically smallest word in my system in this set look like. In particular, does it have any nice structure? Does it have any nice properties? So in this particular, for this particular example, one can show, or more accurately, Curie, Rampersad, Sari, and Zamboni showed in 2013 that the lexicographically smallest point Z with respect to this order is the unique solution to the following equation. So we just look at the point Z such that the second image of Z under the morphism is equal to 0, 1, Z. Okay, so we see that this point Z, which solves this problem in the system, is not exactly a fixed point of phi, but it is very close to being a fixed point or to being a periodic point of phi. Okay, so I think this is not very hard to believe, since phi was of constant length 2, that this Z is again 2 automatic. And in general, several authors proved the following theorem. So starting with some substitution and a coding, fixing some total order on my outcome alphabet, and fixing some letter B in this alphabet, we can look at the set of all lexicographically smallest sequences in my system, which starts with this chosen letter B. Okay, and ask, are they nice in some way? Okay, this doesn't work. Okay, so in 2009, Alush, Rampersad, and Shalit showed that if the original substitution is of constant length k, then yes, all these sequences are actually k automatic. So we have this kind of closure property here. And a few years later, Curie, Rampersad, Zari, and Zamboni showed that this also holds if it's primitive. And then, of course, you cannot hope to show that it's automatic, but you show that this lexicographically smallest sequence is substitutive. In fact, this theorem in the paper cited in point 2 is a little bit more general. Not even a little bit more. It's more general, but it's still not. It still doesn't give a full solution. And as far as I could tell from looking at the references, this is still not solved in the full generality. Someone will correct me if I'm wrong here, possibly. Okay, so now I want to look, okay, and what I should say is what we are going to look today in this talk are basically sequences of this form. Okay, these are going to be our quasi-fixed points, and we'll show that the fact that they kind of appear in various contexts when someone wants to show that some sequence in some orbit closure is automatic or substitutive is actually not surprising. Okay, but before that, let's look at another example. So here I have another alphabet A for letters, and I have substitution tau, which is given as follows. So this substitution is chosen in a way that I can present some nice properties that I want. So let's say I look at my system X tau as the set I'm interested in, and one says that a subsystem or a subset is transitive if there exists some kind of sequence that generates it. So there exists some sequence Y such that the set big Y once again can be described either as an orbit closure of Y or in this combinatorial way as all sequences in my system such that the language of the sequences is contained in the language of Y. So what we were interested in my old work with Jakub Byszewski and Jakub Konieczny was to understand how well behaved are these transitive subsystems of substitutive or automatic sequences. So we know that you have some sequence Y generating this subsystem, but of course, in general, you can have a lot of these sequences. So thus there exists a sequence which is particularly nice, which generates it. And in this particular example, so this is the question. We want to understand how the transitive subsystems of this system look like. And what we can do is the following. So I look at an image of 0 under my substitution, and I write it as V0W. When V is 0, 1, this red thing here. Between I have 0, and then I have a blue thing 2, 3. Okay, and I can take this point, this word, and I can iterate it under my substitution tau. And if I iterate it and arbitrarily say that my 0 coordinate is here before 0, I get the following two-sided point Z. Yes. And now to describe all the transitive subsystems of my system. Okay, so now it is not very difficult to see the following. So first of all, when I look at this system, we clearly see that we'll have a periodic sequence of 2's in my system, since I can just iterate this 2 infinitely many times and get a constant sequence of 2's. And of course, I can do the same with 3. However, if I look at this point Z, since here I'm working in a one-sided context, what I can do is I can cut this point Z at some point N and consider the following suffix of Z. And any such suffix, this is not difficult to check, gives me a distinct transitive subsystem. In fact, each of these subsystems Zn has the following simple structure. It is just the orbit, a one-sided orbit of the point Zn infinity, together with countably many points, which are more or less, which are ultimately periodic, and come from the fact that I have a periodic sequence of 2, a periodic sequence of 3, and that a word 3, 2 and 2, 3 appear in the language of my system. Okay, but the kind of the moral of this thing is, once again, the way we describe all these nice generating points of my transitive subsystems are about the sequence Z, which satisfies here's the following equation. So Z is just T, is just tau Z shifted 2 times to the left. Okay, so now at this point I will make a definition. I will, for simplicity, assume that my substitution is growing, although it won't be necessary for most of what I will be talking about. It's just going to make things simpler. And I'm going to say that a one-sided or two-sided point is called a quasi-fixed point of a substitution. Well, if it is a fixed point, if it is periodic point of the substitution fixed by some, okay, maybe it's not the best way of saying it. Okay, so if there exists some k and some integer m, such that my point z is the solution of this equation that we see here. Okay, and if my point is one-sided and m is smaller than 0, this okay, this doesn't explain much. This means that I can find some prefix such that such that the z is equal to prefix times phi kz. Okay, prefix of length m. Okay, so some simple properties. It's very easy to see that this set of quasi-fixed points is closed under the left and right shift and under my substitution. If I start with some general substitution, every quasi-fixed point is going to be substitutive. Furthermore, if my substitution is of constant length k, then every such quasi-fixed point is k-automatic. So this is known, and this, I think this result have been rediscovered a few times in different settings. Here you actually have to do something, but it's not very difficult. Okay, and what we showed in our older paper, although we haven't at that time stated in this way, is the following characterization. So starting with some substitutive system, any transitive subsystem of the system is generated by some quasi-fixed point. So in particular, and this was our original goal in this paper, in this part of the paper, this shows that any transitive subsystem of a substitutive system is again generated by some substitutive sequence, and any transitive subsystem of a k-automatic system is once again generated by some k-automatic system, k-automatic sequence. Okay, so these quasi-fixed points kind of appeared in a few different contexts. Other contexts dynamically when they appear is in the study of the so-called asymptotic pairs or asymptotic components in symbolic substitution systems. And they are a useful tool for trying to understand the automorphism group of such systems. Yeah, so this is for people who care about this kind of stuff. But I think even as a purely combinatorial question, it is an interesting question to see what is kind of behind all of these results. Okay, and the name quasi-fixed point. So this quasi-fixed points have been around for a long time. They have been studied by Shalit and Wang in an older paper. There's also a section in a book of Shalit and Alush about them. And more recently, they were studied explicitly in the paper of Béal, Perrin, and Restivo. and they came up with a name of quasi-fixed point, although they are called quasi-fixed points. Their definition was slightly different, so I'll tell you about it in a moment. But what all these results show is that you can characterize these quasi-fixed points in the following way. So I have a point in my shift. Then I say that this point is a quasi-fixed point given by this equation, even only if it is a shift. So shift either in the left or in the right of a two-sided point y, which is of one of the following forms. Either it is just a fixed point of phi, or there exists some letter a, some non-empty words w prime, such that I can write my phi as sorry, this is v v prime, and in the same way we saw before, I can just iterate this phi to get my two-sided sequence. Okay, so I said that, so we see here when we look back at the definition of a quasi-fixed point, so I didn't only want to look at phi, I actually wanted to look at all powers of k. Okay? Of course, this is not a problem because having this description, I just can apply it to a kth power of phi, and then I get a analogous characterization of all quasi-fixed points. However, I should say that the name quasi-fixed point in Brial, Perrin, and Restivo paper was just about points of this form. So when here my k is 1. So in a sense, what would be probably most appropriate is to call the sequences I consider quasi-periodic points of a substitution. But then I really didn't think that introducing a new notion of quasi-periodicity is a good idea. So I kind of just decided to call all the points I consider also quasi-fixed and live with the fact that these definitions are a little bit incongruent. Okay, but we have this characterization. In the end, we are going to be interested only in the quasi-fixed points which live in my shift. But well, here it is easy to see that these quasi-fixed points which appear in point 2 will always be in my shift. And in the first case, my fixed point will be in a shift even only if the word AB lies in the language. Okay. And for one-sided quasi-fixed points, one shows that they are exactly given as infinite suffixes of two-sided quasi-fixed points. So this is a full characterization. Okay, so here is now a general problem. So we saw a few examples when we tried to show that some sequences in orbit closures are substitutive or automatic. So here is a natural question. Let's start with some substitution. Our substitution of constant length. Can we characterize the set of all substitutive and or automatic sequences in my subshift x phi? And here we should be here it should say x phi. In general, one can also put the coding here and ask about that. Okay, so I think you can all predict when I'm going with that, where I'm going with that. And what I'm going to say is, okay, so first remarks. So simple remarks which kind of tell you that possibly there is a nice characterization. Okay, so first of all, most systems generated by substitution will have uncountably many points, like for example, 2-mole system or any uniformly recurrent system, which is not finite. And we know that there are only countably many substitutive sequences. So we know that most of these sequences will not be substitutive. And we also know that there are substitutive sequences other than our fixed points. For example, I can look at any shifts. Okay, and now the result says that if we have, so here is a result for substitution, which is of constant length k. So starting with a substitution of constant length k and starting with some factor map to some other subshift y. So if you do not want to hear about what factor maps, you can just assume that this is a coding. Morally here, it doesn't really make much difference. You can just think about this pi as a coding. And in this case, all the sequences in my system, which are k-atomatic, are exactly given by a coding or an image of the factor map of some quasi-fixed point of phi. So in particular, if I don't have any coding, I'm in a purely substitutive case. My sequence in the orbit closure is k-automatic, even only if it is a quasi-fixed point of my substitution. Furthermore, if I have some y in my system y here, which is non-periodic, then I know that all preimages of y by my factor map pi are quasi-fixed points of phi. So it is clear that here I need to assume that y is non-periodic, since I can imagine a situation when I take an uncountable system and just map it by some coding to one point. Okay, and then clearly it cannot be true that all the preimages are quasi-fixed or are also automatic. However, once you assume non-periodicity, it is true. So more generally, so this holds both for invertible and non-invertible systems. Furthermore, here I wrote k-automatic, but actually here we can show something stronger. So just so if y in my k-automatic system is substitutive, then I actually know that it is going to be k-automatic. So in the sense, wherever we want to characterize automatic or substitutive systems in a constant length substitution system, this is the same. They are going to be the same. And I will say a little bit more about this later. Okay, so some older results also, older result also resolves this for primitive substitutions. So this is a theorem of Holton and Zamboni, and they don't phrase what I'm saying here exactly in the same way, but morally this is what they show, and this is exactly the same statement, assuming that my substitution is a primitive substitution and I have some coding. Then I know that my point pi x is substitutive, even only if x is a quasi-fixed point of phi. So just one small caveat is that they work in a two-sided context, but one can easily derive the one-sided context from it. And furthermore, there's not really explicitly written this part about the preimages, but with the techniques, one can also kind of easily get it. Okay, so now here is the question, and here's the conjecture, which I would be very interested in seeing shown, is what happens with the general substitutions. So as always, the case when I have a completely general substitution, one can assume growing here, but doesn't help much, is distinctly harder than the constant length or primitive case. And I hope to kind of later say a little bit about why I think this is the case, what kind of tools we are missing. So this conjecture says this is exactly the same statement. I would like for a general substitution and a general factor map, you can assume this is a coding, that my substitutive sequences are characterized in the same way by the quasi-fixed points of the original substitution. Okay, so here is a little interlude. So I like to think about these quasi-fixed points which lie in my substitution systems as kind of a rational points. And in a case when my substitution is primitive of constant length, I can actually make it very precise. So what happens here is, okay, so here is a notation for the ring of k-adic integers. So the inverse product of finite groups Z, K and Z. If you have never heard of k-adic integers, you have probably heard of p-adic integers, and you can think about this ring ZK as just as a product of all p-adic integers over primes p which divide k. Okay, these are the same objects. And assuming my substitution is primitive of constant length, and that the system I am given is infinite, one has a continuous surjective map kappa from Y to this ring ZK, such that, well, first of all, let's assume for now that that we have no coding. Okay, so all phi periodic points, in particular all fixed points, are mapped to 0 by kappa. Kappa plays nice with my shift map. This means that kappa of a shifted sequence is just kappa of the sequence plus 1. And here is addition in this ring. And kappa of phi of x, and we also have kind of an interpretation of the multiplicative structures in ZK just by phi. So kappa of tau phi of x is just k times kappa of x. Okay, so we kind of have here a kind of a fine map behind all of this. And here in this ring, I can treat the z integers as a subset of zk. These are going to be sequences here which are eventually constant. And then as long as my integer is coprime with k, I can invert it. Okay, so I have a set of rational points in ZK. And what one gets quite easily from all this previous characterization is that under this assumption, when we have this map, my k-automatic sequences, the k-automatic sequences in my system correspond exactly to the rational point in k-adic integers via this nice map kappa. Okay, so this is one way. So in general, for general substitution, let's say, one won't have such a nice map kappa to some topological group, not thinking even about ring. This happens, for example, when my substitution is weakly mixing. So there are some dynamical constraints for that, but somehow it is still useful to think about these quasi-fixed points in a system as kind of a rational points. Okay, so in the times left, I want to talk a little bit about the proof. I don't really want to actually give the full proof. I just want to talk about what kind of tools go into it, and then what kind of tools are missing, or at least I don't know about them for the general case. So here is just a reminder of what we are trying to prove. We first assume that my substitution has constant length k. And I want to describe all k-automatic sequences or automatic sequences as quasi-fixed points. Well, we know that quasi-fixed points are k-automatic. This is easy. So what we are really trying to show is that all automatic sequences in my given system Y are of the required form. So are quasi-fixed points if I don't have a coding, or quasi-fixed points and coding if I have a coding. Okay, so first of all, why? So here I said just automatic. So first of all, we can assume that the base is the same. And this is due to a very classical result, which I paraphrased here a little bit by Fagnon, a generalization of Cobham's theorem, which says that if my system is k-automatic, so it is generated by some k-automatic sequence, and I have other sequence there, which is automatic with respect to some base, then it actually has to be k-automatic. So in general, if the sequence is periodic, then I know that it's actually k-automatic with respect to any base k, and the hard part is to take care of the rest, which is what this theorem does. And in general, from my work with Clemens Müllner on hidden automatic sequences, it will basically follow that if Z is substitutive, then here, if the Z is substitutive, then it is in fact k-automatic. However, it says will because this is still not yet finished. But here, these notions of automaticity or substitutivity in a substitutive system, in an automatic sequence, are going to be the same. So we can assume that base is however close to the original substitution as we want. It's the same base. We are working in the same numeration system. And another proposition is the small thing, which is basically to take care of this factor map or a coding. So what it says is if I start with a substitution of constant length of some constant length, then I can find a uniform constant big K such that every factor map from X phi to some other system Y or any coding is K to 1 on non-periodic points. So it means that the fibers of these points on non-periodic points Y have cardinality at most K. And once again, it is crucial here to assume that Y is non-periodic. Otherwise, I can just map everything to a constant sequence. And if the starting thing was uncountable, then I won't get it. Okay, so this basically handles morally it handles this factor map coding pi. So we can assume kind of for the rest of this presentation here in the constant length that we are working in a purely automatic case, or purely substitutive. And for automatic sequences, we have the following nice kind of finite characterization of automaticity, which is inherent to the sequence. And this is well known. This is just the kernel characterization of automaticity. So if you've never heard about this, it basically says that my sequence is k-automatic, even only if well-defined set of subsequences of this sequence is finite, and this set of subsequences kind of depend very highly on this base k. And what you can do with this is, well, we want to take a sequence z in my system, which is k-automatic, and we want to show that it has to be a quasi-fixed point. Well, since it is k-automatic, I can assume that its k-kernel is finite. Now, because this is not going to be a proof, this is just really going to be a kind of a snap picture of why this works here. Because the base of my sequence Z is k, which is also the length of the substitution, you can write this the elements of the kernel of the sequence Z very nicely in terms of this substitution. And what it gives you is that using the finiteness of these kernels, some counting arguments, some pigeonholing, and critical factorization theorem, you basically show that enough of these finite things have to overlap to tell you that Z has to be a quasi-fixed point of phi. Okay? And so for critical factorization theorem, just to show what this is probably known for most people here, but maybe not for everyone. And this is a very nice result. So I called it critical factorization theorem. It's actually more of a corollary of a critical factorization theorem. And it says that if I have an alphabet and a finite set of non-empty words of size d, okay, so d is the size of this finite set, not the size of the words. So I have a set of size d of finite non-empty words, and I have some sequence, two-sided sequence here, which is non-periodic. Then this sequence X has at most d W factorizations with pairwise disjoint cut. So what it says is if I take my sequence X and I try to write it as a concatenation of words from W, and I write it in a way such that the endings and beginnings of these words in different factorizations are never on the same index, then I can do this in at most d ways. Okay, so this is a classical result. And in the context of a substitutive system, a very closely related result is what is called recognizability. And it says that for any substitution and any non-periodic point in my two-sided here substitutive system, I can always find a unique point in my subsystem and a unique integer n, which is smaller than the length of phi of the first letter of the point x prime, such that my x is uniquely substituted using n and x prime. Okay, so what you get here, which you do not have here, is really a uniqueness. So you don't only know that you have kind of finitely many of this factorization with respect to phi of A, but you know that it is really unique. As long as you are kind of looking at these factorizations which come from your system. However, once you have, for example, a coding or a factor map, then in general, it doesn't work. So if you are not in a purely morphic, purely substitutive context, then the uniqueness is not necessarily true, and then maybe you actually want to use critical factorization theorem. So here there is sometimes the recognizability but is better, sometimes this more general critical factorization theorem result is more useful to use, but this works in general. These are general statements which work for any two-sided substitutions. So now when we go, so this was like a synopsis of what happens when I look at the substitution of constant length. So now what happens when I have primitive substitutions? So once again, I have the same statement. Now I assume that my substitution is primitive. I have some coding, and I want to describe all substitutive sequences in my system as these quasi-fixed points or codings of them. Okay, so here I could assume that the base of my sequence Y is the same as the base of original substitution phi, but it is not really needed for the proof. And I also haven't told you what the base is in this general case, so let me skip it for now. So to take care of the factor maps or the codings, we have exactly the same statement, which was proven by Durand in more generality for so-called linearly recurrent systems. And it basically says that if I start with a primitive substitution, then there exists some uniform constant such that every factor map to some infinite system is k to 1. And here I don't have periodic points because periodic points are kind of hidden in this infinite system. Since Y has to be minimal, if it has a periodic point, it has to be finite. Okay, so this is the same result if my phi is primitive substitutive, not of constant length. And one has a very nice inherent characterization of primitive substitutivity, okay, of primitive, of being given by a primitive substitution due to Durand. And it says the following. So here we are going to start with an example. Here I have some sequence, which I think may be even the 2-Morse sequence. And I look at some prefix. Here I have chosen prefix U01. And I look at return words to this prefix. So I look at all words which start with 01, and 01 doesn't appear again in this word. So here appears only once in this word. So here I see I have 011. Here I see I have another 0, so I start another a new cut, and I have 010. Here I see I have another 01. So I have another word 0110. Okay, and here I have another 01, and so on. So if you start doing this, because my original sequence is uniform, the word appears bounded gap. I know that I have finitely many of these return words, and here they are given by these 4 words, which I have seen at the beginning. Now I put labels of my return words to the prefix U, labeling them by the alphabet 0, 1, 2, 3, and how many I had them, putting the labels just in the order they appeared. Okay, so here 0, 1, 1 is going to be 0, 0, 1, 0, 1, the next one is 2, and the next one is 3. And now I just rewrite the sequence, putting, instead of this return words, these labels. And this is the so-called derived sequence of X with respect to the prefix U. So now you can do this for all prefixes U of your sequence. And what this characterization of Fabian says is that if you start with a uniformly recurrent sequence, so you start with a sequence in which every word appears with bounded gap, then you know that the sequence X is primitive substitutive, even only if the set of these derived sequences as with respect to U, as U is any prefix of your sequence, is actually finite. Okay, so not only you know that you have uniformly bounded sizes of this return words to all prefixes, but you know that they kind of appear in this bounded kind of way. And once again, this is a characterization which kind of doesn't see the substitution. Of course, you can, using the finiteness of this derived set of this derived sequences, you can compute this substitution. However, this is something inherently in the sequence when you know that the substitution exists, but you only look kind of at the sequence. And then, no surprisingly, this is what was used originally in Holton and Zamboni paper to prove the result I stated. Okay, so now what about this general question? And I see I don't have much time. Just unfortunate, so I'm going to be try to be more brief. So this is once again exactly the same statement when I would like it to be true for a general substitution. And this is a conjecture, this is a question. I don't know how to show it. What I know is that it's actually enough to show that any y, sequence y in my system, which is substitutive, and which generates y. So this language is the same as the language of y, is of required form. So without the coding is a quasi-fixed point of a substitution. And this basically follows from this characterization of transitive subsystems of the original system I stated a long time ago. Okay, so you can kind of assume that the sequence you want to show to be a quasi-fixed point actually generates the same language as your system, because you can pass to subsystems. Okay, so now what I would mean by a base of a substitutive sequence, so I'm going to be brief here. When one can look with any substitution, one can introduce a certain incidence matrix. In the case of constant length substitution, this matrix has dominant eigenvalue k. In general, it has some dominant eigenvalue, which is some parent number, say alpha, and then I say that phi is an alpha substitution. And now my sequence is going to be called alpha substitutive, so this is a definition due to Durand, I think. Well, if there exists an alpha substitution, a fixed point of this alpha substitution such that all letters from my alphabet appear in this fixed point. This is a very important assumption here, and some coding such that my sequence is given as a coding of this fixed point. And the generalization of Cobham's theorem given by Durand says that if I have a sequence which is alpha substitutive and beta substitutive, then either the sequence has to be ultimately periodic, or alpha and beta are multiplicatively dependent. However, as far as I know, there's no in literature, there's no language version of this theorem, and I'm not sure if this would follow kind of easily from the papers of Durand and Michel Rigaud. So what would it say? So this is the second question. Or conjecture. If we start with two real numbers, pair of real numbers, and I have a sequence which is alpha substitutive and other sequence y which is beta substitutive, and I assume that the languages of the sequences are the same, well, I would want to have the same results. I would like to know that either alpha and beta have to be multiplicatively dependent, or they have to be ultimately periodic. That would mean that I can reduce to the case when the base of my sequence in my system is the same as my substitution. Yes, this is a remark that we cannot here assume that the language is only a subset of the language of y, because we can when my substitution is uniform, I can kind of easily get something which is of smaller value here. And just to recap, this is known in the case when my sequence is automatic. This is Finesse theorem, but this is also known when they are primitive substitutive. And this kind of the best proof of this I know kind of uses ergodic theory. Okay, so this seems like it seems like this conjecture too would be helpful to prove the first conjecture, so the general characterization of substitutive sequences in my system via quasi-fixed points. Actually, one can show that this first conjecture implies this second conjecture, using, of course, Fabian-Duron's result. And this basically is because any quasi-fixed point of my alpha substitution, as long as it generates the whole system, is going to be alpha substitutive. Okay, so other question, do we have the following statement which lets us pass to which kind of takes care of the coding or the factor map? I don't know. Presumably it should be true. We know a lot about recognizability and similar results, but I'm not aware of any such statement in the literature. And last, the most important part, I don't really know about any inherent nice finite tree characterization of substitutivity, which it would be suitable in this context, in the same way kernel, K kernels or derived sequences were in the previous ones. And since my time is up, I think I will just finish with a remark that I kind of realized when preparing this talk that I will be talking to an audience which probably knows a lot about abstract numeration systems. So one could ask if this following conjecture becomes easier if I don't want to characterize all substitutive sequences, but I only want to characterize sequences which are automatic with respect to the same abstract numeration system as the one of the original substitution. Maybe this helps. Okay, so I think I will stop at this point. Thank you very much for listening.
Thank you very much, Ella. Does anyone have any questions? Hajime.
Thank you for a nice talk. And I have a question about chaotic integers. So you've mentioned chaotic integers and a map from map kappa. So
yeah, I call it kappa.
Kappa. So I'm sorry if I misunderstood, but is it possible to write this kappa explicitly?
Yes, so by the way, once I introduce it, this is not my invention, this is kind of well known, at least when the tau is when there is no coding, the fact that this map exists is due to an old result of decking. And when I have a coding, this is basically due to Clemens, Müller, and Riemann-Yasawi, but basically with the same proof. So yes, one can write it. So the question is, what do you mean by explicitly? But one can write it when one knows about recognizability. So what happens is there was recognizability at some point. This is a problem, so this was later. Now, when was here? Okay, so you have this recognizability result. So assume here that your substitution phi is of constant length. Okay?
Okay.
And you start with some point x. And you want to understand what is the image of this x by kappa to k-adic integers. So what you do, you can find this x prime and this n, which here is between 0 and k, such that this holds. And then you do the same for x prime, and you do the same for the sequence you got from x prime and so on, and you got an infinite sequence of integers between 0 and k. And this basically gives you a k-adic expansion of the point kappa x. And this is well known, but if you look at the paper on archive of the stuff, I also have written down with the details, everything there.
Thank you.
Jean-Paul has a question.
I don't hear you. Yeah.
Can you hear me?
Oh, yeah.
Okay. Thanks
Yeah,
for
now
your
I
talk.
can hear you, yes.
Thank you for your talk. Dziękuję. Yeah, I have a question about your conjecture that not number 1 or number 2, but the very first one you said at the beginning of your talk, I mean, in the first half. You had some results for the automatic sequences, and then you said that it would be great if the same thing we're holding for morphic sequences. Do you see what I mean?
Yes, yes. And I mean the kind of the part at the end was basically about why I cannot prove it. Yes.
Okay. My question was, do you have any idea of a family of sequences for which it would be true? I mean, it's true for automatic sequences. Maybe if you add an hypothesis like morphic sequences being primitive or being piezo or whatever, maybe you can do something. Can you?
Well, I mean, so there's a guess about what is true and what can be done. So
Yeah.
my guess is that it should be true in the whole generality. Yeah.
Absolutely.
So but what can I do? Well, for primitive morphic, it is done. I basically have also done it. I actually started this project a long time ago. And I also did the primitive case before I kind of realized that it is in the literature, but it was kind of hard it's hard to know about these results until you kind of find them or ask someone. But not, I mean, so I think the case which would be the easiest is if you start, if you start with a substitution such that all letters have the same growth rate.
I see. Okay.
This would probably help a lot. Another question I have, so one could actually change this question a little bit, and starting with a general substitution, one could, so I don't know this stuff very well, but from what I understand, there is a one-to-one correspondence between substitutive or morphic sequences and abstract numeration systems. And in this way, all k-automatic sequences basically correspond to k-adic expansion, a standard k-adic k-nary numeration system. So starting with a substitution and its fixed point and a coding, which gives you a given numeration system, the first question is, if I look at all quasi-fixed points which generate the system, are they once again automatic with respect to the same numeration system? It's hard to check. And if they are, well, then maybe it is actually easier to prove that. And from what I know is there's actually the same kind of kernel-like characterization of S automatic sequences when this S is this abstract numeration system. So maybe one could just take this and the proof would follow the same line. I don't know that much about abstract numeration systems, but that would be one way, would be a generalization of my result, and would kind of circumvent this hard question about multiplicative independence, which are kind of hidden here. Yes.
Okay. Thank you. Thank you very much. Thanks.
Are there any other questions? Anna Frid just had a question in the chat. She just has a colleague who's very interested in this stuff, so she would like a copy of your slides for the
Sure,
website.
I will send you the slides, and I guess the slides and the talk are usually in the kind of the archive of a
Yeah, that's right.
of a seminar anyway. But sure, I can also send it. And you said that this is who?
Oh, Anna Frid was asking.
Anna Frid.
Yeah.
Yeah, sure. So I will just send you the slides and you can put the talk. I think you recorded it. So
Yes, thank you. I just always collect the slides, and this time I need it not because I need it for the seminar page, but because I'm really interested.
yeah, so there are two reasons to collect the slides.
Yes, exactly. Both.
All right. Well, thank you again, Ella.
Thank you very much, and sorry for taking this long on the last talk before the summer and maybe vacations for you.
No, it was a really great talk to end this session of the seminar. So yeah, thanks a lot, and we'll take a little break and start again in September. So thanks everyone for coming.